Hello everyone, this is Mumuksh Tahil and we are back with another video. This time we are going to discuss on Jetson DLA hardware. By DLA we mean Deep Learning Accelerator. Yes, this is a hardware available on board on the NVIDIA Jetson devices. Moving on to what exactly are DLA cores. Well, DLA is a dedicated specialized hardware accelerator core which is available on board for NVIDIA Jetson devices and is generally used for computing convolutional neural networks, as this hardware device is actually hardwired for solving convolutional neural networks. Well, DLA cores are specifically designed to consume less power with a very reasonable trade-off for performance that CUDA cores can offer in general. And while you might think, why would I want to trade my performance with lower power consumption? I have a lot of power budget, and why would I ever even think of trading it off with performance? Well, there have been a lot of edge AI-based applications coming up in recent times, whether it's about autonomous vehicles or small and smart mobility devices like drones. Everywhere AI is required, and in such cases, you require such uh, accelerated, low power consuming edge AI devices which can help you with such applications. So, coming on to the hardware as well as the software level support that DLA offers. Uh, DLA hardware is specifically designed while focusing on convolution layer, deconvolution layer, pooling layer, best normalization layer, and a lot of other operations as well. And you can find out this specific hardware accelerator on board on the NVIDIA Orin as well as the NVIDIA Xavier uh, lineup of the Jetson devices. And more generally, they have up to two DLA cores on board. Moving on to the software side of things, well, the DLA software stack offers DLA compiler and DLA runtime, which is pretty much built into the TensorRT uh, stack. And you can pretty much easily use TensorRT. You can invoke DLA compilers and runtime by using the unified common interface offered by TensorRT. And TensorRT can actually be used for any of your AI inferencing based tasks. Now let's move on to an example. Here we're going to consider the results from one of the papers that I submitted and which also got accepted at the IEEE International Conference on High Performance Computing, Data and Analytics. The paper is evaluating multi-instance DNA inferencing on multiple accelerators of an edge device. This is one of my own papers, and along with under the guidance of my supervisor, my research supervisor, Professor Yogesh Suman. Let's consider this example. We are looking at model ResNet 50, and the framework that we're specifically going to focus on is PyTorch. These are the three different precisions, data precisions that we are looking towards. FP16, that is half precision, FP32 full precision, and AMP. AMP is a very different, newly developed precision by NVIDIA, and it stands for Automatic Mixed Precision. It is kind of a hybrid between FP16 and FP32. If you want to know a bit more in detail about AMP, you can definitely check out the previous video on tensor cores. Apart from this, we are also going to consider different batch sizes from 1 till 64, and for all these experiments, the concurrency is going to be set at 2. By concurrency, I mean there would be two separate processes running in parallel at all times. Now let's consider this graph observed from the results that were generated for the scenario that we discussed in the previous slide. A couple of these bar graphs have already been discussed in the previous video on tensor cores. However, in this video, we are going to talk about the remaining two bar graphs that we couldn't discuss or we did not intentionally discuss in the previous video. These two group of bar graphs, have something in common, and that is that these results have been generated by also using DLA cores. So if you actually compare these results, overall you might see that for bigger batch sizes, CUDA plus tensor is the best combination that you can actually use. So there is actually no need of using DLA cores when you are straight away going for bigger batch sizes. And it also makes sense because ultimately you are with DLA cores, you are trying to trade off your performance with lower power consumption. So with bigger batch sizes, it would be expected that you require a lot more powerful hardware to do so. And DLA, on the other hand, is pretty much trying to uh, offer you low power consumption based solution. So obviously, CUDA plus Tensor is good for bigger batch sizes. But then if you're not looking for a very big batch size, let's say you are only interested in inferencing batch size 1, 2, 4, something of that order, and you are good with that, in those cases, it doesn't really make sense to use just CUDA cores or CUDA plus tensor combination. You can always, in such scenarios, start considering DLA available on the NVIDIA Jetson devices, because NVIDIA DLA cores, they are specifically designed once again for low power consumption. They are specifically designed to dedicate the performance dedicatedly for improving the performance on lower power budgets. And when dealing with smaller batch sizes, you can expect lower power consumption, and hence, in such scenarios, DLA comes up on top. You can clearly see that CUDA plus DLA performs really good when you are dealing with batch size 1, 2, 4, as compared to CUDA plus tensor combination. On the other hand, let's say if you're not really sure about what's the batch size that you're going to run your inference for, let's say you are running a server, you are offering a service where people can themselves go and uh, decide what batch size they want to run their inference on. Well, in those cases, uh, you can always use the complete combination of CUDA plus tensor plus DLA all running at once. And what this means is that you might not be getting the best performance that you could get with either of the two already available combinations. That is, you might not be able to get as good a performance as CUDA plus tensor cores uh, when operating on bigger batch sizes, as well as you might not be able to match the results of CUDA plus DLA when running on smaller batch sizes. But in general, the software stack or the compilers coming from NVIDIA are smart enough to keep and maintain a balance such that uh, you don't have to trade off a lot of performance while keeping things simple for you. So you can just simply go ahead, enable all three available hardware devices or hardware accelerators on board. Just use all of them. If you're not really sure of what what batch size for inference you can expect, uh, then for sure you can go with CUDA plus tensor plus DLA. But if you're not really aware, if you're really sure of if you're going to use a very small batch size of 1, 2, 4 something, then you can decide to go with CUDA plus DLA combination. And for bigger batch sizes, you can specifically decide to go with CUDA plus tensor combination. So are there any references for how you can use CUDA, for how you can use DLA cores? Well, sure. We have all the required uh, links for you. You can uh, go check out the TensorRT video for knowing a bit more on how TensorRT and DLA are mixed, are packed up together, and how TensorRT makes things easier for you while using DLA codes. You can also know a bit more about DLA by going through the article that I've attached here. There's also this available official GitHub repository by NVIDIA for deep learning workloads. It also covers a lot about the DLA hardware and how you can use it. Finally, there is also this publicly available documentation by NVIDIA, which specifically talks about how you can program your NVIDIA DLA codes. So you can check these out. All these links I will be adding in the description, so you can check them out from there. And with that getting said, thank you for watching this video. If you liked it, please do make sure to like the video. And also, if you have any concerns, you can definitely comment down in the comment section. Thank you.